Now we want to look at the topics about the Taylor polynomials. First, let's look at some definitions. Let I be a neighborhood of xi, x0, sub-0, and f and g are the two functions defined on I. Then f and g are said to have contact of order 0 at x sub 0 if f of x0 equals g of f x0. F and g are said to have contact of order n at x0. So here this n is a natural number if the case derivative of f at x0 is equal to the case derivative of g at x0 when k is greater than equal to 0, less than equal to n. K cannot greater than n. So this is the definition for the order of contact of two functions. Now let's look at the example. So this is the function f of x equals the square root 2 minus x squared, and the function g is equal to e to the 1 minus x on the interval I, which is from 0 to square root 2. And we noted that f of 1 is equal to g of 1, right? If you plug in x equals 1, right, which each one is equal to 0. If we take the derivative of f, x, which is equal to negative 2x over 2 square root 2 minus x squared, right? So it's equal to negative 1 over square root 2 minus x squared. G prime is equal to negative e to the 1 minus x, right? So if you plug in 1 again, f prime of 1, which is equal to negative 1, right? Which is also equal to g prime of 1. However, if you continue to take the derivative, the second derivative of f at 1, which is not equal to the second derivative of g at 1. So these two functions, f and g, have contact of order 1, not 2. So now let's look at some some formulas, okay, for the calculation for the case derivative. So here is the formula. The case derivative of what? Of x minus x naught to the L's power. L and k are integers or positive integers and non-negative integers. It's equal to two cases. If k is not equal to L, then it's equal to 0. If k is equal to L, it's equal to k factorial. You can try some numbers to see why this is true. Okay. So now let's look at the proposition. So we still let I be a neighborhood of x0, and we suppose f has n derivatives on I. There exists a unique, this means there exists a unique polynomial of degree at most n that has contact of order n with f at x0. So this polynomial is p denoted by p sub n of x, which can be written as f of x naught plus f prime of x naught times x minus x naught, and going on, continue, then the last term would be f the nth derivative of f at x naught over n factorial times x minus x naught to the n. So now let's look at the proof for this proposition. So the first case is n equals 1, n equals 0, right? When n equals 0, so p sub 0 which is of x, which is equal to what? Equal to f of x now, right? So the result is very clear, right? So now we consider n greater than equal to 1. So we take the differentiation, okay, for the polynomial p sub n, then you will see that the p sub n to the kth derivative, of course k is less than or equal to n of x, which what's that, okay? So we want to see if this is equal to the kth derivative of f at x naught. So this would be can be written as this is the same thing, right? Of p sub n of x when x equals x naught. And if you do the calculation, we use this formula, right? You will see it's equal to, for the left side, we take the derivative for this left side case derivative for the right side, sorry, the right side, then you will see it's equal to f the case derivative at x naught. So here k is from 0 to n. Okay, so this function and the polynomial p sub n have contact of order n at x naught. So f and p sub n have contact of n of order n, order n at x naught. So this is we prove the existence, right? So now we want to prove the uniqueness. What is the uniqueness? So we suppose we have a general polynomial. P is a polynomial of degree at most n. So P is a polynomial of degree at most n. It can be written in the powers of x minus x naught as, so p x is equal to c naught, so we let p is equal to c naught times c1 x minus x naught plus c2 times x minus x naught square, then plus continue plus cn x minus x naught to the nth power. Then we want to show this constant C0, C1, C2 to Cn are these numbers f of x naught, f prime of x naught, and f, the nth derivative of f at x naught over n factorial. So now let's take the case derivative. Okay, let's take the case derivative. We still use the formula we have. It will evaluate at x naught, right? So the case derivative, we know this one has a contact of order n with f of x. So this one must be equal to the case derivative at x naught, right? This is from the assumption we have, right? And on the other hand, if we use the formula, we take the derivative, the case derivative on the right side, right? Then you will see it's equal to k factorial times c sub k. If you plug in x equals x naught. Then you compare both sides. It will tell you that c sub k is equal to f, the case derivative at x naught over k factorial. Right? So here k is from 0 to n. So that means, this p of x must be equal to the p sub n of x, where this p sub nx is given by this formula. So we finish the proof. There is no other choice.